All right, good afternoon and welcome to the IACS seminar. Some of you already met me. I'm Pavlos Protobabas. I'm the scientific director of the program. The IACS seminar are kind of enhancing the education of the master students here, plus to the bigger community. We bring topics in computational science and data science in general. And it doesn't have one theme. We have a bunch of different things and different subjects and different angles to it. Today, it's my honor to introduce Ben Brown. He is an assistant professor at the Department of Astronomy and Planetary Science at University of Colorado, Boulder. Right? He received his bachelor's from Harvey Mudd College in Los Angeles. I didn't know where it was at. So it was in New York, but he told me. And a Ph.D. again in planetary science for CU Boulder in 2009. What he is known is about this amazing open source code that does all kind of PDEs, fluids and other things. And the talk today will be describing that amazing piece of work. Please welcome Ben to our seminar.
Thank you all for having me here. I'm very excited to be here, and I'm very excited to talk about this really fun collaboration that I've gotten to be involved in the last couple years. One of my principal collaborators is actually in the audience here, Jeff Oishi. His picture is at the top there in the left. He's sitting right here in the front, and he lives here in Boston and works up in Maine, and so is an excellent local source for building collaborations on this and is one of the main principal architects of this thing. I just break stuff with it and make pretty movies, and so I'm going to show you pretty movies and the different experiments we've done to break things. This is a collaboration of 5 of us. The gray pictures on the left there all got together about 7 years ago and started creating this open source platform for solving partial differential equations. I'm going to show you a little bit about how we got here, what our motivations were, what the tool can do, and this movie that's playing is a fluid dynamical experiment of convection at the top and internal gravity wave driving at the bottom, and we'll talk about that a little bit towards the end of sort of astrophysically motivated fluid dynamics experiments, including some work done by a number of my students. Students get to show up in color. Old gray beards show up in black and white. So there you go. Anyway, so let me tell you very briefly about astrophysical fluid dynamics and our star, the sun that we live near, and just how little we know about the interior of the sun and how cool and crazy it is. So the sun, here's a cartoon view on the left side. The sun, the very center of the sun, is a fusion burning nuclear reactor. The inner 2/3 of the sun, the energy of nuclear fusion, is carried out very slowly and gently by the radiative diffusion of photons. It takes about 1 million years for energy generated in the center of the sun to percolate its way out to about 2/3 of the way out in radius. The center of that core is about 15 million degrees Kelvin. That's very, very hot. At about 2/3 of a radius, you've dropped to about 1 million degrees Kelvin, and the plasma is actually getting cold enough that it starts to become opaque to that radiation. The opaque plasma blocks the light from carrying the heat, and now the plasma itself starts going into large-scale bulk instabilities and motions of convection, and it is the material plasma itself that now carries heat up to the surface where it can effectively radiate and cool again. The outer third of the sun is this convection region, where the swirly things are here. So we see the very surface of the sun. We see convective patterns on the surface of the sun. There are these things we call granules that are about 1 megameter in size, 1 million meters. That's about the size of either France or Texas, depending on your background and preferences. Those structures churn every 5 minutes. So every 5 minutes, a France-sized convective blob is appearing and disappearing on the surface of the sun. We see structures that are about 30 times that big that churn once a day. And we believe that there should be structures that span the outer third of the sun, the full convection zone. And for those, we have essentially no observational evidence whatsoever, despite tremendous efforts looking for them. What we do have observationally for the interior of the sun is we actually have pretty good maps of the large-scale fluid dynamical flows. And this is because the surface of the sun ripples in sound waves, and there's a science called helioseismology that allows you to use sound waves observed at the surface of the sun in the way that it Doppler shifts the light at the surface to infer the fluid properties and flows in the interior. And with those, we can map the interior flows, and we have found that the interior of the sun rotates in some ways that are very odd for objects like the Earth. The equator rotates around once every 25 days. The pole goes around more slowly, once every 35 days. And there's a large-scale angular velocity gradient from the pole to the equator of the sun that we see from the surface and extending inwards radially throughout that outer third of the star that's the convection zone. Cool. This large-scale differential rotation is the first large-scale flow created by the turbulent convection. It's something we'd really like to understand. The rainbow picture in the upper right is our observational measurements of it, which are extremely well constrained, and they look completely different than theorists predicted before we actually saw them. So there you go. So the sun has all sorts of beautiful puzzles. The biggest puzzles right now for the deep interior of the sun are questions of how strong are the convective motions in the interior? How much do they fight rotation? How much are they constrained by rotation? What's the rotational constraint of the interior? And when our convection zone comes to the interior where the photons carry the energy, where that dashed line is, it changes from this shearing, rotating body to one that rotates like the Earth, all at the same rate, all at the same speed. What happens at that internal boundary layer? What are the properties of it? We have thought for a long time that the sunspots and magnetic fields that we see at the sun have their origins in that deep layer. So if that's true, what's going on down there? We don't really know answers to either of these. We've studied the sun for 400 years since Galileo. We've had amazing helioseismic measurements of the interior for the last 40 years, roughly. There are still profound open questions about the interior of the sun. It's the nearest stratified astrophysical object other than the Earth's atmosphere that we can really interact with. And to give you an idea of just how wide our disagreements are, the plot on the left are a couple of different observational constraints on fluid properties in the interior of the sun. The orange line and the red line, the ones with error bars, those are observations. The orange line is a claimed upper limit on the speed of flows in the interior. The red line, using the same data from the same satellite but different inversion techniques, is a claimed detection. They differ by 2 orders of magnitude. The blue and purple lines are, or the green and purple lines are simulations. And you might say, hey, those simulations and the red lines, they all look pretty good, but they still differ by a factor of 2 to 4, which is more than enough in rotating fluid dynamics to give you a solution that's completely obviously wrong. Unambiguously, obviously wrong. And the convection simulations, as we have gotten better at doing them, they have gotten in worse and worse agreement with what we actually see. And so there are profound things we don't understand about the interior of the sun. These reflect just absolutely huge disagreements between our turbulence models, mixing length theories, and other ways of approximating the convection with the actual underlying dynamics. So they're beautiful problems here. So how do we study these? So the way that we tend to study motions in the deep interior of the sun, motions in the deep interior of the sun are slow compared to the speed of sound, but they have extreme density stratification over the domain where the motions happen. The base of the convection zone of the sun is 14 density scale heights. So 14 e to the 14 times denser than the density at the top. 14 density scale heights, 14 e foldings in density. And it's a factor of like 2 million or so. So the motions have a lot of stratification, but they are very, very, very slow. The speed of sound is like 200 kilometers a second in the deep interior of the sun. The flows are probably hundreds of meters a second. So factors of 10 to the 5 between the sound speed and the flow speed. So they're stratified, but they equilibrate extremely quickly to the background. So how do you study flows like this? So there's a hierarchy of constrained models that take the Navier-Stokes equations of fluid dynamics, the PDEs, and apply a constraint to them, usually by way of the continuity equation, to try and filter out the sound waves. And this, for a long time, was the only way to study these systems that have large-scale stratification but slow motions. There's a hierarchy of these constraints. You may be familiar with the Boussinesq equations. Who has seen anything of Rayleigh-Benard convection or Boussinesq equations ever in their lives? Raise your hands high and proud. High and proud, a very small number, very good. So we'll see a little tiny bit of Boussinesq convection later on. This is where the constraint is that the flow is incompressible. You squeeze things together, it squishes out. Divergence of the velocity field is 0. When you introduce a large-scale non-constant coefficient like a density stratification, your divergence of the velocity can now be formed by that background stratification. So in, say, an anelastic approximation, rather than the divergence of density, or of u being 0, it's now the divergence of the product of density times velocity. The divergence of the mass flux is 0, the divergence of the momentum. That's our first approximation to adding stratification. You can go further. Here's a generalized pseudo-incompressible equation that is what really started Jeff and I and others on our exploration of solving new partial differential equations. So we've known for a long time how to solve the top equations, the Boussinesq equations. We've also known for a long time how to solve the middle equations, anelastic equations. That was really technology discovered in the 60s or so. The generalized pseudo-incompressible equations, no one really had an idea of how to solve it, and there weren't existing codes to solve it. And we tried to adapt existing codes to solve it and had just nightmares. And this raised a question for us, how do we solve new and interesting systems of equations in astrophysics? And this led us to the development of what we have called the Dedalus framework, which is a toolkit for solving partial differential equations. So the fact that we had a variety of different problems that we wanted to solve led us to developing a generalized tool for the solution of specific classes of PDEs, rather than building yet another domain-specific astrophysical code that solved one particular set of PDEs. And this is really transformative. Jeff is really deeply influential in the fact that we have a generalized toolkit rather than having gone running off to go and solve yet another specialized class of problems. We created, and I'm going to show you a little of this, essentially a language for expressing PDEs, where the toolkit will take that language for your PDE expression and turn it into the underlying numerics to solve the system in a way that divorces you as the user somewhat from the questions of spatial discretization compared to the problem that you want to solve. And this lets you also do consistent comparisons between different types of PDEs in the same numerical framework, rather than being like, well, I have one solution from one collaborator and another solution from another collaborator, and how do I actually make them talk to each other? I'm lost. So this is an openly available thing. We've got a website, dedalusproject.org. We have open email lists for our user support, and our principal, so there's all of us standing in Santa Barbara many, many years ago. I had less gray hair and shorter hair. Here's our principal code architect, Keaton Burns. Keaton was a grad student at MIT. He's now a postdoc at the Simon Center for Computational Astrophysics in New York. And Keaton is the lead author and coder of this. And you'll see sort of the roles of all of us within this collaboration as we go forward. I'm going to show you some slides that Keaton, Jeff, and Daniel Leconet developed for a presentation at the Simon Center, the Flatiron Institute, sort of discussing some of the overall properties of Dedalus and where we got started. So we started this in about 2011. And at that phase of time, this is when Git and Mercurial distributed version control software platforms were relatively mature. They had about 6 years of life under them at this point. But they really had not come into the world of theoretical astrophysics. The state of the art in the world of theoretical astrophysics was sort of 100,000 line legacy C++ and Fortran codes. If you were extremely lucky, those were version controlled in a like Subversion or old school CVS. and the prevalence of modern computing and coding was more or less non-existent in theoretical astrophysics. Our overall goal was to use Python, this newfangled language, and to make a simple and hackable platform where we could play and experiment with fluid dynamics problems that we were interested in. We wanted to bring in modern development techniques, and we were heavily inspired by a number of astrophysical projects that were community codes, the ENSO cosmology code, the YT visualization platform, and the pencil code out of Nordida. And these were sort of nascent open source projects. YT was particularly influential for us. Jeff and Keaton, Jeff Uishi and Keaton Burns got together first. They created the first formulation of this. At that point, it was essentially an MHD solver using Python and using some libraries and toolkits for doing the actual hard lifting computationally. About 2012 is when myself, Jeff Vassell, and Daniel all finally joined. This brought in ideas of generalized discretizations and generalized equations, moving from a specific MHD equation to a more general class of solutions. Here are all of us being crazy characters. 2013 was when we made the second version of this, where a principal goal was to minimize our source code so we could make it as flexible as possible. And then about 2014 was our first methods paper. The first external packages came out a few years later, and in the last year, we've really started hitting extremely different geometries and much more interesting mathematics. As of last year, there were about 30 papers published using this tool, and what's really interesting is only 12 of them were published with none of us in the original collaboration having had any interaction with the authors. So these are people who have found it on their own and created solutions on their own and reached a publishable state with essentially none of our internal domain expertise, which has also gotten to be fairly substantial over this time. All right, so what does sort of the base package do? So the key ideas, one is that the equations are generalized and are entered in a symbolic fashion. So the problem that you are solving can be adapted as you find different ways of asking about it. And there are different toolkits for actually doing a solution to your PDEs. You can either do time-stepping initial value problems, you can do nonlinear boundary value problems for sort of equilibrium solutions, you can do eigenvalue problems to study linearized response of the system, do instability studies, do wave studies. Another sort of key feature is high accuracy. We use spectrally accurate methods. I'll show you a brief little bit about that in case you haven't done much with global methods. It's an extremely high performance tool. The back end produces sparse matrices. We write things to do the equation interpretation, but we rely on libraries to actually do the computation. And so all of the computation that is happening is C or Fortran fast at the level of like the basic linear algebra subsystem and FFTW. Like we're not going to make that any faster. And it compares extremely well with domain-specific codes. It's written in Python, and it automatically MPI parallelizes, and you can run this thing on a 3D problem on as many cores as you have access to. You can run on, we've run on 64,000 cores, sort of a Potemkin village exercise. Practically speaking, we do runs at 4,000 to 16,000 cores regularly. If you had 1 million cores, you could run on that. We don't choose to do those kinds of problems. We've generally been reduced to simple geometries, and you really need, there's no magic here. You must have a partial differential equation that is resolvable on the system you're trying to solve it on. You can't rely on numerical smoothers or other things like that to give you a good solution, which is either a pro or a con. I view it as a pro. The basic idea of a global spectral method, who's seen global spectral methods in any fashion? the same number who had seen Boussinesq, Rayleigh, Bernard, more or less. So the idea of a global spectral method is that you use trial functions, basis functions, in your computation, and you expand your solution across your basis functions. And I'll show you a couple of them in a moment. So you use connected large-scale basis functions. The equations that you're solving are really projected against those basis functions, and then you solve in this sort of projected coefficient space, and this works for both linear terms and nonlinear terms. This is a methodology that's easy to adapt to different equations, but it's usually restricted to simple geometries because they are dictated by the basis functions that you have available to you, which tend to be polynomial classes. A lovely thing about spectral methods is that if you have a smooth solution, these show exponential convergence. And so to some extent, as soon as it looks good to your eye, it tends to also be good basically to machine precision. So factor of 2 changes take you to something that looks terrible to your eye and so is obviously wrong to something that's as good as your computer can possibly do anyways, given the techniques you have. So that's a nice property. These are not adaptive methods. So these really are best suited when you have interesting dynamics everywhere in your domain that you want to resolve, rather than extremely interesting dynamics in a very small region and then some far field solution you're trying to get. So the kind of most basic of these is to use Fourier series basis functions. These work nicely for periodic structures. They have very fast transforms. They have a very simple matrix structure. And you take a whole bunch of different basis functions in rainbow colors and you co-add them together in a weighted way to get some interesting structure. Okay? So Fourier decompositions. Slightly more advanced, Chebyshev polynomials. So Chebyshev polynomials are sort of like a half series of the Fouriers. They're like the cosine series. Chebyshev polynomials do not require periodicity, and so with Chebyshev polynomials, you can apply arbitrary boundary conditions if you use a tau method and solve your matrices in the right kind of way. They still have exponential convergence. You still have fast transforms because they're still kind of like half of a Fourier series, so you can still use the discrete cosine transforms. But a really big problem with Chebyshev methods up until now is that Chebyshev methods have always had very dense matrices. And this is because the derivatives of the Chebyshev polynomial don't project onto a single Chebyshev polynomial. They have broad bandwidth. And so you have these horrible dense matrices to solve, and they're very, very poorly conditioned. And so Chebyshev methods are often limited to a small number of polynomials, a couple hundred, maybe 1,000. So they're very lovely. We had a really major breakthrough and major insight. This came out of work by Keith Julian at University of Colorado, Alex Townsend and Oliver Sheehan, and Jeff Vassell in our collaboration, the applied mathematician, really sort of brought this to our attention. So if you try and represent a Chebyshev derivative, dx of polynomial t sub j, a derivative acting on the Chebyshevs, if you try and represent those derivatives using the Chebyshev basis functions themselves, you get a dense matrix. Here's the dense matrix. The filled in points are the places that have coefficient power. It's very broad bandwidth. Now conversely, if you represent the Chebyshev derivative not using a Chebyshev polynomial, but using the second kind of Chebyshev polynomials, the U polynomials, then you get an optimally sparse representation. It's diagonal. Pow. There's the insight, right? Use the right basis functions for the right operators. Don't use the same basis function for everything. Sometimes you want to change your basis functions. This is the sort of tremendous insight, and this just leads to amazing power all the way into spherical systems. And it really leads to sparse matrices that can be solved with arbitrary boundary conditions on them. So not just periodic systems. This is kind of cool. Okay, so what's the user see when solving a problem in Dedalus? So here's an actual set of equations from Boussinesq Rayleigh-Benard solution, effectively. This is incompressible hydrodynamics. The top 3 lines of Python code are laying out the 2-dimensional domain that the PDE is going to be solved on. The 3rd line sets up the solution technique to be used, an initial value problem with a set of variables. There's some parameters of the problem. It's a constant coefficient problem. It's got 3 parameters there. And then the system has 4 equations. There's a horizontal momentum equation with U, a vertical momentum equation with W, a divergence of U equals 0 constraint, the 3rd equation, and then a first-order formalism, a connection of vorticity to the underlying equations to create sparsity. So high-order PDEs here are being solved by representation as a coupled set of first-order systems. That's one bit. There's also there's a grammar. So there are text strings being entered for the equations. There's a grammar that is specifying time derivatives, dt's. There's a grammar specifying spatial derivatives, dz's and dx's. Those are inheriting the coordinate system from the domains that are specified at the top. So as a user, you can use whatever coordinates you like. And there's some constraint equations as well. So the approach here is a parsed grammar, a string language that you interact with as a user so that you spend your time playing with equation representation questions rather than playing with what the heck is my discretization of the time derivative question. That's handled through sort of different time steppers brought into the system. And different time steppers can be tested against each other all under the same framework. So you're removed from it being directly interacting with that, and you can then flexibly change that. The goal is to have you focus on the problem rather than on the technique. One other thing is that terms on the left-hand side of the equal sign are all linear in the variables of the problem, possibly with non-constant coefficients. Terms on the right-hand side are not necessarily linear in the variables to be solved. And this represents an underlying break in the time stepping between explicitly stepped terms and implicitly stepped terms. So there's an implicit, explicit machinery for time stepping, which gives some tremendous power in the problems to be solved. For something like a simple wave equation, going from what you enter as the user at the top there, the text structure, the basic pathway is that text is parsed through an infrastructure to make an operator form. The operators are then turned into matrices that are linked to your underlying spatial and temporal discretization. And then those matrices are the things that actually time evolve the solution or lead to other solution techniques, EVPs, and boundary value problems. The under the hood structure, so as the user, you interact with something like the green script in the upper right, the script implementing your equations, Rayleigh-Benard. The infrastructure that we've written is the stuff in the middle layer in the boxes, ways of interpreting the equations into different solution techniques, ways of bringing different basis functions into them to solve Chebyshev's, Fourier, things for spheres, the polynomial representation and the solvers. And then that comes down onto the fast libraries being provided through NumPy, SciPy, FFTW, and other sort of as fast as they can be implementations. Okay. In terms of parallelism, in general, you can parallelize these things across the dimensions separated from the basis function. So if I have a 3D problem, I can split that up in 2 dimensions as long as I have 1 dimension of contiguous information for evaluating something like the polynomial transforms. And what this practically means is that for like 1,000 cubed problems, you can run those on sort of millions of cores. And if you have 2D problems at sort of 1,000 squared, you can run those on thousands of cores, more or less. If you have a 1D problem, that runs on a single core. So if you go to higher dimensional problems, you can apply more and more computing power to it. If you're wild enough to do 6-dimensional plasma physics, you could parallelize it over 5 dimensions and keep DOE and others very happy with their computers. For the actual solution technique, the right-hand sides in particular, which have non-constant coefficients and nonlinear terms, those have to be evaluated in different spaces. You have to evaluate derivatives in coefficient spaces to get spectral accuracy. You evaluate products and other nonlinearities in physical space. This is generally called a pseudo-spectral technique. And our solution to handle general possible terms on the right-hand side is to create operator trees and to sort of search through them to figure out the optimal way, more or less, to get your answer in going back and forth between those spaces, because the transforms from physical to coefficient space is the price that you are paying for being able to have the spectral technique. So you want to reduce those, and there's some very clever infrastructure for doing that. Okay, so what are some fun things we can do? Here's a nonlinear Schrödinger equation solved on a network of coupled nodes. So this is a finite amplitude Schrödinger equation with a nonlinear term, and here it's propagating around a defined network of nodes to see what the resulting solution would be. That's kind of cute and kind of fun. This is solved as a set of coupled one-dimensional equations, one for each leg, and then the nodes are handled by boundary conditions between Chebyshev domains. And so there's something like 20 domains being solved here all simultaneously. Nice small problem. This was a toy problem that we did just kind of for fun. Yeah.
What do you show here? Is it?
This is the wave packet amplitude for the nonlinear Schrödinger equation. Yeah. In this geometry, given these defined lengths. Yeah.
Where electrons, atoms at the corners, is it anywhere?
Who knows what's at the corners? Here's another nice problem. This is done by Keaton as part of his thesis. This is like Rayleigh-Benard convection turned on its side. This is glacial melt for glaciers. So you have a vertically oriented ice sheet here. It's melting, and it's in a stratified salt ocean here. And you get fingering layers that reach out into the horizontally, even as gravity drives the actual dynamics vertically at that sidewall. This is an interesting problem for trying to understand the rate of melt of ice and glaciers, because these layers then actually form directed fluxes of hot and cold water into the wall. And so the melt rate shown jitteringly here on the right is dependent on that layer structure. And you can actually see this in real glaciers. That's kind of cute. So geometrically, this is actually a Chebyshev domain this way with boundary conditions here, and then outflow boundary condition here, I think. And then vertically, it's actually a periodic domain wrapping around itself, which seems to work for this problem, and sort of interesting properties of layer formations. All right, so here's kind of a cute one. This is a immersed-boundary method in a spectral code for studying a boat driving itself in a stratified ocean. This is a boat with a constant force motor on it. And as the boat goes along, it drives an internal gravity wave behind it that eventually grabs the boat and stops it. This is a two-dimensional model of dead water in Norwegian fjords. It is the correct model for a two-dimensional boat, whether that has anything to do with actual dead water phenomena or not. But the way that this is being done to actually capture a hull is with a volume penalized immersed boundary method. And then you see the sweeper going along here. That's going along just to sweep out the eddies, so the front eddies, when they wrap around periodically, don't run into the boat. You actually do this kind of thing in a spectral method. And this was done by a master's student in Sydney, Australia, as kind of a lark. This isn't even his main thesis project at this point. So, you know, fun things. It's a boat. It's a boat. In the last year, our really big effort has been to take our nice boxes, which are simple, and translate these into spherical geometries. I'm going to show you a little bit about this and then some of the science we've been doing with this. So this is work that's really led by Jeff Vassal, our applied mathematician, and Daniel Le-Cohenet, who is going to be starting a faculty position in applied mathematics at Northwestern. just learned that a couple of days ago. So these two did a tremendous amount of work on these spherical approaches. These say 18. They're actually just published in Journal of Computational Physics 2019. They were about 2 years in review. And these are two beautiful and massive papers on solving tensor equations in spheres. I'm going to show you a little tiny bit about it. Here are two benchmark solutions that we've done using our code, and they've been tested against known benchmarks to an accuracy of better than 10 to the minus 6, roughly. So we actually know that these solution techniques work. They're not just sort of pretty pictures. So these are volume renderings of some different swirly things. Okay, so what's the story in spheres? So one thing that we've learned kind of over and over again is that if you generalize the problem, you often pay a cost in the generalization, but sometimes then reap huge rewards in the ways you can use it. So the generalization that we found for spheres is that you go from our typical scalar spherical harmonic basis functions, and you incorporate what are called spin-weighted spherical harmonic basis functions. These are spherical basis functions with an additional index and degree of freedom. And if you do this, then your gradient operators and your tensors project onto those spin-weighted spherical basis functions in a sparse fashion that is relatively simple to solve. It's like a Fourier series with an extra index running around, a spin index. So you have to do a lot of, you have to do some fanciness to know how you go from one spin basis to another and kind of keep track of the bookkeeping and the algebra, but it's basically just bookkeeping and algebra and 2 40-page JCompPhys papers. But the kind of underlying basis function, so here's a L2 M2 spin 0 basis function at the top, which you may have seen at some point in your lives. And here's the L2 M2 spin 2 basis function, which I had never seen in my life, and that like otherwise shows up in like LIGO gravitational wave stuff occasionally and a few other places. These end up being the beautiful and correct way to do fluid dynamics on the sphere. So they make the system quite lovely. And there are two absolutely lovely papers that are now published open access in JCompPhys. So I am never satisfied to just stop with the things that actually work. I like to break things and make them challenging. Here's that same full spherical domain. So the advantage is that you can do now a domain that captures all of a sphere and also goes to the r equals 0 singularity at the center of a sphere in a correct and contiguous fashion. And this movie that's playing in the upper left is taking those sort of simple constant coefficient systems and now adding a very large non-constant coefficient in radius to represent a large-scale density stratification, solving anelastic equations in the full sphere in a rotating domain for studying dynamo problems, because our friends in the front row here who are stellar astrophysicists would dearly love some dynamo solutions for stars that look something like this. And we have none of these because we've never been able to do them before. But you can do these solutions. So the colors here, the red is hot stuff that buoyantly wants to go upwards. The blue stuff is cold stuff that wants to sink towards the interior. The whole thing's in a rotating reference frame, and it builds its own large-scale internal flows and winds. And this is one slice out of the large-scale 3D spherical solution that was all calculated using those very tensorial projection techniques. And a toolkit that we are publishing and releasing openly to anyone who wants to use it. We have the constant coefficient version is already out. The non-constant coefficient version that I like playing with, we're still in the process of breaking and understanding what does and doesn't work, but is basically in a functional mode. And here are some vector magnetic field line renderings from a dynamo solution related to this thing, sort of showing large-scale magnetic fields that are created in an MHD solution. Okay, cute. I still have my tag on this from January. We were pushing for a spring publication, and we got caught by the federal shutdown because it shut down all of the NASA supercomputers. So neat things that we've been able to do with a generalized framework like this. At the beginning, I showed you a set of constrained equations we wanted to solve. We had a new third equation we didn't know how to solve. We were like, hey, let's make some infrastructure for building it. We built the infrastructure, and then we realized that we didn't have to solve the problem we were limited to. We could solve a much more interesting problem. So these are the full Navier-Stokes equations, the actual compressible equations of fluid dynamics, written in a special way. And the pink underlined terms on the left-hand side are terms that correspond to the large-scale non-constant coefficients of like the Earth's atmosphere or the interior of the sun. These are the large-scale stratification that affects the solution and that leads to really interesting differences between upflows and downflows and some other things I'll show you. The equations that are here are exact. There is not an approximation that has been made in terms of dropping small terms. I haven't written the viscous term or some other things like that. Oh, I guess I actually have. There's the divergence of pi. But these are exact. These have not approximated the thermodynamics, which is what the closures are usually doing in the constrained equations, and in a way where we don't know anything about the outcome of the thermodynamics. Here, the full nonlinear thermodynamics are here. We've just basically moved a term. We've subtracted out a term that we hope is a big term and moved it from one side of an equation to the other. We've moved it from an explicit treatment to an implicit treatment. It turns out that this actually lets you go and solve these fully compressible equations in a low Mach number limit. So why is that hard? These equations have sound waves running around through them. The sound waves set your numerical time-stepping constraints normally, and usually you have to follow the sound waves. Here, we've effectively moved the sound waves into a portion of the equations we can handle linearly and implicitly. And so long as those terms well represent those dynamics, then the solution should be stable. And it turns out it is in experiments and benchmarks that we've done. And what's lovely is that like this took a fair bit of work to do on understanding the equations level, but once you've done the math and figured out the equations, the computational cost is not much more expensive than the other approaches for solving this kind of problem. It's like 50% more expensive than using the inelastic simulations, but that's really just because you're solving more actual equations. Because you want to keep those thermodynamic variables, you have to solve equations for them. And so you're solving more equations, so your cost goes up with the number of equations. There's no magic in the cost, and things work extremely, extremely well. So we thought this was a good idea. Daniel went and actually tested whether it was a good idea. He did this lovely piece in 2016, taking an existing astrophysical code called the Athena code, very, very popular and well-known code, huge community of users, extremely different approaches, finite difference techniques, Godunov methods for shock capturing, and did spectrally accurate Dedalus simulations and did a benchmark problem between the two of them for two-dimensional nonlinear Kelvin-Helmholtz roll-up in domains that did or did not have density jumps. And the pictures on the left are on the right here. These are the pictures of the solutions and how they compare. Here's the spectrally accurate ones. Here's the Athena ones. They're very nice. They look the same. They're periodic. So when one solution maps onto the other in a smooth way, that means they're visually capturing the same thing. This has about 2,000 coefficients per dimension. This has about 16,000 coefficients per dimension. So the spectral approach gets you a little bit in terms of cost. This costs 20,000 CPU hours. This costs north of 2 million to get to the same solution. And what was fascinating was Daniel did L2 error norms of essentially a dye entropy through the solution. And he found that the Athena solution started out the red, and then the orange, and then they kind of converged down onto the Dedalus solution. Okay, so that's not too surprising. That's a convergence of a finite difference method. But what was very surprising was that up until you hit a pretty high resolution, even the green line didn't capture it here, they really took off in some weird direction. Turns out the finite difference Athena solutions were converging onto a different physical solution and then staying there. and only when you got them sufficiently high in resolution did they converge to the right basin of attraction that the spectrally accurate solutions were finding. And you could demonstrate this and demonstrate the basins of attraction and demonstrate that the ones that you thought were just fine in finite difference were being kicked there by grid scale noise that was driving them to the wrong physical regime, which is either lovely or terrifying depending on where you live. So that was a very nice piece of work. It really kind of pointed out the utility of carefully constructed benchmarks. I want to show you, I think, one more thing, which is sort of experiments in convection, especially with non-constant coefficients. So I'm going to start you out with a movie of two-dimensional Rayleigh-Benard convection. I'm doing 2D movies here because the movies turn out very nicely for these solutions. 3D is fine, but very difficult to see in a projected format. So here's a 2D solution of Rayleigh-Benard convection. The red stuff is hot and it goes up. The blue stuff is cold and it falls down. This is a Rayleigh number of like 10 to the 8. So the Reynolds number is like a couple hundred to 1,000 or so. It makes kind of nice little pretty structures. The momentum equation for Boosted-esque convection, you've got this buoyancy forcing just on the right-hand side of the equal sign, the temperature forcing here. And that's why hot things go up and cold things go down. Hot things have a positive temperature perturbation. Cold things have a negative temperature perturbation. And it drives the equation in a very obvious way. Lovely. Here is the same kind of phenomena in a fully compressible set of equations in a stratified atmosphere at low Mach numbers. So here you have, again, red things, hot going up, blue things, cold going down. Now the relevant thermodynamic variable is not temperature, but entropy. That's fine. And the kind of very interesting difference between the solution at the top and the solution down here is that here the upflow and the downflow have broken symmetries. The upflow is big and wide. The downflow is narrow. It's also faster. So you have sort of slow, gentle upflows and fast, vigorous downflows. OK. This structural change is coming about because of the non-constant coefficients in the problem, especially the density stratification. Lovely. So Evan Anders, who's one of our students at University of Colorado, got interested in these stratified convection problems and in asking, hey, are these stratified convection problems similar to or different than our understanding of simple Rayleigh-Benard convection with constant coefficients? And Evan did some really lovely work in a 2017 PhysRev Fluids and then in a 2019 AppJ paper with Jeff and I on non-rotating and rotating convection, showing that even though you have the complications of stratification and stuff like that, that the ideas of Rayleigh-Benard convection still print through, at least in the kinds of parameter regimes that we can access. And they print through amazingly well. The plot in the middle is a parameter space plot of what's called the Nusselt number, and they show the exact same sort of 2/7 scalings that we know classically from laboratory experiments and classic Rayleigh-Benard problems. Lovely. Here's some movies of that same kind of thing. So the top rows are laminar solutions, so low Reynolds numbers. The bottom rows are more turbulent solutions, still just in 2D here. And the left and the right are the Mach number differences, low Mach number at left, high Mach number at right. And the left and right panels are almost indistinguishable from each other. And the bottom and top panels, you see the difference in scale structure. In fact, the only way you can actually tell the difference in the Mach numbers of these is that if you look very closely at this lower right panel, every now and then you'll see a solid front move across it. Those are shock waves sweeping across the solution. So you can occasionally see shock waves coming out of the cold downflows. There's a throat, and as the flow goes into the throat and gets cold, it booms supersonically and sends a shock wave racing out behind it. And that's more or less the only physical difference you can tell between the two systems. That's fascinating. We thought they would be completely different from each other. They're indistinguishable from each other. That's fascinating. That's a surprise. OK. Jet, another of our grad students, has done some lovely work bringing in chemistry and bringing in reactions And that's all lovely too. I'll show Pavlos this later on. Let me get you to a last idea. I want to leave you with a couple of thoughts from our kind of collective work on this open source collaboration over about the last now 8 years almost. One is that reproducing numerical solutions and experiments is really hard. And this is really crippling in theoretical astrophysics, and it's going to become increasingly crippling in other fields if you haven't grappled with this already. In Astro in particular, the standards for reproducibility of theoretical work is really lax. And this is a conversation that we are trying to change. To some extent, if you cannot reproduce existing computational work, then that work does not have scientific validity, right? And so it's important that we figure out ways to actually make our computational scientific work reproducible. Open source tools help tremendously in that. It's extremely hard to reproduce closed source results from published information in the literature. We've spent months on various problems doing this, and sometimes find problems in the underlying solution. So open source tools help, but they are not sufficient. You actually have to publish effectively the full tool chain to get to a set of results, because I could give you the Dedalus pseudospectral framework. It's open source. Reproducing our work on stratified convection is much, much, much harder. It took us about 3 years of constant investment to get to the spot where we are now. That's a huge investment. That's $500,000 at startup level funding at a university in terms of person power to get to. So it's important that we publish more of our solutions than just the underlying tool that makes them. That's been something that we've been trying to really push. With modern approaches and modern coding approaches, you can build a community code on the relative cheap. So we estimated, very roughly speaking, that Dedalus has probably cost about $2 million in-kind contributions of effort, startup funding from 3 faculty members in different ways. A lot of that's the person time that's been put in by all of us, and especially by Daniel Leconet and Keaton Burns, who've been kind of prize postdocs and able to contribute a lot. $2 million or so. In contrast, the astrophysical flash code had a price tag north of $100 million, according to the person who helped found that. And there are downsides when you do it on the cheap. We don't come with a manual. We are trying still to write our instrumentation paper describing how the code works, now like 7 years after it's been in production. But those limitations do not stop you from creating an open source community code and supporting it for a community of hundreds and hundreds of users. And if you want to get an idea of sort of what it's been like in our project to do this, Jeff wrote a really nice white paper last year that's on arXiv, documenting sort of what it's been like to support a code like this, how many users we have, and what sort of the person cost has been in maintaining the user lists. All right. Thank you all for your time. We've hit 2:30. I will hang out and answer as many questions as you like, but thank you very much for your time. Yeah, then anyone else can come and find me. So
you don't have to do anything special with shocks, because they're not new shocks.
So long as the physics in your PDE is able to regularize the shocks, so long as it is an actually resolved physical solution, nothing special. So this solution has a whole bunch of shocks whipping around in the upper half of it, and here's a zoom in on one of them. That is actually a viscously mediated shock at the parameters the problem is at. As long as you have something like that, then you can do it, and if you don't, you can't, right? No. But yeah, there's no magic once the thing is a resolved solution. So
how many cores does like this run on, for example?
500 cores for like maybe 24 hours.
And it's MPI parallelized. Is it also within the nodes parallelized with some shared memory? Or
Not right now. Other than whatever the underlying MPI library itself does automatically, which a fair number of them do at this point. Yeah, yeah. So, but no, it's an MPI parallelization. Pavlos.
Silly question. Why is Flash not open source? I mean, isn't it funded by
Yes.
NASA and everything? Should it be available to all of us?
Is that because of its bomb heritage, Jeff? Yeah.
Is what?
It was developed by the NNSA, the National Nuclear Security Agency.
Okay.
We have never been funded by the NNSA, so we can be fully open source. So.
The motivation was to explore explosions not in the astrophysical sense.
Yeah.
See what I mean?
Yeah, I think that's why they have a controlled open source approach where they give it to you, but you have to apply.
You have to be a citizen to use it.
You have to be a citizen. Okay.
Yeah.
Thank you.
Yeah. So.